All right, friends, welcome back. In this video, we're going to be taking a look at section 5.4 of your textbook, and just like to apologize in advance. You might hear some nasaliness in my voice. I'm getting over some cold symptoms here, but hopefully that won't be too much of a distractor here in the video, because in this video, what we want to do is talk about exponential equations. And so I want to go ahead and introduce to you a couple of the different cases that you'll be up against whenever you have exponentials in your equation and you're asked to solve for the variable. And so I'd like to just go ahead and dive into that. So the first case that you'll be up against are cases of exponential equations where the bases perfectly match up and are the same number, okay? So for example here, if you ever have an equation where that base number b equals that base number b on the other side, then what you're automatically able to say is that if you want the left-hand side to equal the right-hand side, then the only way that that's going to work when the bases match up is if the exponents also match up. And that's exactly what it says right here. So those are the easiest types of exponential equations to solve, or when the bases match up. It's going to be a little bit more challenging whenever the bases don't match up. And in that case, we're going to have to ask ourselves a different question here. So if you take a look at this first example, example 1, it just says solve the exponential equation. In part A, we have 8 to the x power is equal to 2 to the power of 5x plus 2. And you'll notice here that the bases don't match up at all, right? We have a base of 8 and we have a base of 2. Obviously, 8 is not the same number as 2. And so that presents a little bit of a question to us. Like, how do we continue from here if the bases don't match? Well, the point of the question is we can go ahead and get the bases to match if we go ahead and do a substitution for that base of 8 right there. You know that the base is 2 on the other side, so maybe one of the things that you could do is take 8 and rewrite it so that it is an exponential with a base of 2. And so if you think about that a little bit, we could take 8 and rewrite that as 2 to the power of 3. And so if we go ahead and perform that substitution, call 8 2 to the power of 3, then that allows us to go ahead and write the left-hand side as 2 to the power of 3 raised to the power of x. And that's going to equal 2 to the power of 5x plus 2 on the right-hand side that was originally there. And then we can go ahead and continue to do this by remembering our exponent rules, right? So on the left-hand side, we have 2 raised to the third power, further raised to the power of x. If we have power to power like that, what we always do is we multiply those exponents. And so that's going to give us 2 to the power of 3x on the left-hand side, and then, of course, that's equal to the right-hand side. And this is very, very good because now we've rewritten this to the point where now the bases do perfectly match up. And so this gives us the ability to go ahead and say that if I want this to be an equation, then I have to have the case where these exponents are now equal to each other. So we are literally just going to go ahead and drop those bases of 2, and we're just going to go ahead and set those exponents equal to each other, and then continue to solve this like an original equation like this. And so in order to do that, we just need to go ahead and get our x's to match up here. So subtract 5x from both sides. We're going to get negative 2x is equal to 2. And then, of course, divide both sides by negative 2, and we'll get our final result here. So that's going to be x is equal to negative 1, and that is going to be the only answer that we have to this equation, okay? Now, one of the things that you're able to do is you're able to check if this solution is actually a solution of your equation by using the calculator, okay? I'm going to demonstrate this in the TI-84 just because it has neat little functionality that allows us to check an answer really easily. If you're using another calculator, feel free to either see me or send me a message, and I'll work with you the best I can to get you to a point where you can check these in your calculator. But let's go ahead and go to the TI-84 here. It's been a while since we've checked an answer here in the calculator, so let's go ahead and review that one more time here. So we just got an answer of negative 1. So what I'm going to do is just go ahead and type in negative 1 into the calculator here. And then I'm going to use the function of the TI-84 that allows us to store that value into a variable. And so the store button is right next to the number 1 button. It says STO with an arrow. And once you press it, you'll notice it puts a little arrow character in there. We're going to store that into a variable. And I'm just going to press the variable button that's sitting right next to your green alpha button. And then press enter here. And what you've just done is you've just gone ahead and stored negative 1 into that X button. So now when you press this X button, it's just like you're pressing a negative 1 button, okay? And so what we're going to do here is we're going to go ahead and type in both sides of our equation, and we're going to see if we end up with the same number, right? So we're going to type in 8 to the power of x, and then we're going to type in 2 to the power of 5x plus 2, and we're going to see if we get the same number, okay? So 8 to the power of x is going to give us this number right here. It's not so important what that number is. We just need to make sure that we get the same number when we type in the other side, which is 2 to the power of 5x plus 2. Make sure I type it in right. 5x plus 2. There we go. And then press enter, and we can see that we get the exact same number for both sides of our equation, which is what we want. So we can confirm that this really was a solution to our equation here. So that's pretty nice. A couple of these other examples here are basically the ones that are in the same vein. So part B, very, very similar problem. You notice that I've already done it here for the sake of time in the video. But I'm going to take that 27 and I'm going to rewrite that as 3 to the power of 3, just so I can have some matching bases of 3 on both sides of my equation here, okay? I might have some power to power. I might have to multiply those exponents out like I do here. I have 3 times 2x. That's going to give me a 6x there on the left-hand side. And then once I have those matching bases of 3, I could just go ahead and set those exponents equal to each other and then solve from there. And you notice that I get a fraction as my answer here. That's okay. Sometimes we're going to end up with fractions as answers, but that's no problem. We literally just want to go ahead and perform that exact same method there to solve the equation that we're going to be right as rain, okay? Here in the next example, we have 2 to the x power is equal to 64. So obviously those bases don't match. 2 and 64 are not the same number, but we can get that 64 to be rewritten with a base of 2, right? And go ahead and rewrite this as 2 to the x power is equal to 2 to some power. We want to brainstorm on that. How many 2's multiply to make a 64? You could either take out the calculator and start experimenting, start multiplying a bunch of 2's out and seeing how many make a 64. I'll give away the punchline here. It's going to be 2 to the 6th power that actually ends up being 64. So because we now have the bases matching up, they're both 2, we can now just go ahead and literally set the exponents equal, and funny enough, the answer just kind of falls out on this problem. That's going to be x is equal to 6, okay? So really easy way to solve the problem there. Again, your goal is to try to get those bases to match up if they don't already. Here in the next example, we have part D. We have a decimal number, so on the right-hand side, we have 0.0001. This is just one of those things where you can rewrite that using a base of 10, but you're going to need a negative exponent. Thinking back to like scientific notation that we talked about earlier this year, or in a science class that you might have had from before. So we can go ahead and rewrite the right-hand side as 10 to the power of negative 4, and now that we have like bases of 10, we can go ahead and set those exponents equal to each other, and the answer just kind of falls out of that one as well. X is equal to negative 4. Here in the next example, we have bases that don't match, and so we want to try to see if we can rewrite these bases so that they have bases that do match. And the problem here is that 8 is not something that you could take multiple copies of and multiply to make a 32. If you just had one copy of 8, obviously that doesn't get you up to 32. If you had 2 copies of 8 multiplied, that would get you up to 64, which is well beyond 32. And so that presents a unique type of problem here. What we're going to have to do is we're going to have to take 8 and 32 and see if we could break those down into a smaller base that they might have in common, right? And so you could go ahead and do that by taking 8 and replacing that with 2 to the 3rd power like we did in the previous example. And then 32, you can go ahead and break that up into 5 copies of 2. So that'll be 2 to the 5th copy, or sorry, 2 to the 5th power I meant. There we go. And we can go ahead and perform those substitutions there, and that will make it so that we have the same base of 2 on the left and the right-hand side. And now we just have power to power on both sides. We could just go through and multiply those exponents. So that'll be 2 to the 3x power on the left, and that'll be 2 to the power of 5 times that expression, x minus 1 on the right. And now again, since we have those common bases of 2, we could literally just drop those bases and just set the exponents equal to each other. So that's going to be 3x is equal to 5 times x minus 1. And then we would just continue to solve this in the usual way. The next step of this would be to go ahead and perform some distributive property there on the right-hand side. That's going to give us 5x minus 5. And that's going to be equal to 3x. And so the rest of this just works out in the exact same way as we've seen in the previous examples, and this is a straightforward linear equation from Algebra 1. And so I'll just share with you what the final result is going to be here. You're going to end up with 5 over 2 as your final result. Okay? And again, I haven't been checking my answers as I'm going through here in the calculator, but you could be doing that yourself in the TID4 if you like. Here in part F, we have a little bit of a unique situation where we're going to have to remember one of our previous exponent rules to help us out with this one a little bit, because you notice that I've got this number of 1/5 in the problem, right? One of the exponent rules that we used to talk about was your negative exponent rule, and what this did was it allowed us to go ahead and rewrite a fraction like 1 over 5 as an exponent with a, as a base to some exponent, right? So this is your negative exponent rule that we talked about back in your exponent chapter, okay? What that allows us to do is it allows us to go ahead and take that 1/5 and rewrite that as a base of 5 to the power of negative 1 in an example like this. And so now you can see that I've rewritten both sides as a base of 5 to some power after rewriting that 25 as 5 squared. And then I can go ahead and just set my exponents equal and then solve from there. So that's going to be one of the things that might pop up if you ever have a fraction like 1 over a number. Just remember that you could always rewrite that as that number to the power of negative 1, okay? So these are just a couple of examples here where we have an exponential equation and the bases don't quite match up, but we can do some work to get those bases to match up, okay? Kind of begs the question, what if you have some examples where you cannot get the bases to match up, okay? Well, in that case, we have what's on the back here. So when the bases are not equal, here are a couple of guidelines that you can go ahead and follow to go ahead and make those problems a little bit easier for you to solve. So the very first bullet point here says the first thing that you want to do in all cases is you want to isolate that exponential on one side completely by itself. And of course, by exponential, we mean that base raised to that exponent of whatever, okay? And so if you're taking a look at an example like down here in part A and of example 2, we see here that we have this exponential right here. We have this 2 to the x power, and it's completely by itself, right? We don't see any extra numbers times out front. We don't see any extra numbers being subtracted, like a -4 in back or anything like that. It's just base of 2 to a power of x by itself, done, okay? If that's the case, the way that we're going to solve this is we're going to remember a previous set of notes here, and that's going to be our 5.2 notes, where we were actually practicing how to convert from exponential language to logarithm language. And so if you need to go back and watch that 5.2 video, I might recommend that you go ahead and watch that part of it, because in that video what we talked about is how to take an expression like this 6 squared is equal to 36. That statement, we can rewrite that in the terms of the language of logarithms and say log base 6 of 36 is equal to 2. So if you need to go back and rewatch that video, I might recommend that you do that, because that's going to be the exact method that we're going to perform to solve an equation like this, okay? So we have just one exponential in the problem. The base of that exponential is a 2, and so for that reason, I'm going to go ahead and start my log off here with a base of 2, okay? And the way that we go ahead and convert this is we go ahead and loop around here, right? So that'll be a log base 2 of 10 is equal to x. So log base 2 of 10 is equal to x, in which case x just kind of fell out there. We know that x is just simply going to be equal to the log base 2 of 10, and we can go ahead and plug that into the calculator to get a nice decimal approximation for that, okay? So if you're in the TI-84, again, the way that you pull that up is you want to press alpha, window, and then the number 5 key, because you can see that it's the 5th item in that list. And then you can just type in your base of 2 and your input of 10, and then press enter here, and we're going to get this decimal number right here. So about 3.322 is going to be our final result. If you don't have access to the TI-84, then one of the things you could do is use that change of base formula that we also talked about in your 5.2 notes, and that'll give you the ability to go ahead and evaluate the log of any base, okay? And so I might go ahead and recommend that you refer back to that set of notes for that, all right? Another example of this would be in the case of part B here. You notice that the exponential that you have here is 3 to the x power, but you have this extra plus 2 in the back. And so we're going to need to get rid of that first before we start looping around and changing that language to logarithm language to solve the equation. So you can see how that shakes out there in part B. We're going to take care of part C here in a second, but before we do that, I just want to show you a couple of other examples where we need to isolate that exponential first. And so here in part D, we have an extra 11 times in front, and so that is going to be something that we're going to get rid of by dividing both sides by 11 first to start us off, and then we can go ahead and loop around to change that language. You notice that the other part of this is after we loop around, we have that extra plus 1 in the back of x there. We can go ahead and get rid of that by subtracting 1 from both sides, and then we get our final result. It's going to be a negative decimal here, 0.7177. Another example of that would be part E here, where we have Euler's number to the power of x, so that's e to the x. And then again, same thing. We want to get rid of that 3 times out in front. We want to get rid of that minus 5 out in back. And so we're just going to get rid of that minus first by adding 5 to both sides. And then after that, dividing both sides by 3. And then we can go ahead and loop around to change that language here. The other note I want to make about part E here is that when you do loop that around, that's going to be a log base E. Keep in mind we give that a special name. We call that your natural log. And so you see there that I'm doing the ln of 26 over 3 instead of writing out log log base of E. That's our natural log there. And to be honest with you, I'm not sure what part F is doing on this side of the notes. This actually belongs on the reverse side of the notes where we can get those bases to match up here. So here's the work for that. I'm not going to dive too far into that. You can go ahead and pause the screen and read through that one on your own if you like. But what I'm going to go ahead and do here is part C, which is going to be probably the most challenging problem we'll do in the video today. And I want you to kind of remind yourself why, right? So this would be an example where the bases don't match up. We can't really write the two bases in terms of each other, and they don't really break down in terms of a simpler base, okay? This is actually not even one where we're able to convert the language to log language because we have two different exponentials in the problem. And so in order to solve one like this, what I want you to go ahead and do is refer back up here to your bullet points where it says in the second one, take either the natural log or the common log of both sides of the equation. And as an extra little note there, I want you to go ahead and write this down in your notes. We're only going to perform that if we have two different exponentials in the problem and we can't get those bases to match up, okay? And so make that extra little note there in this problem here, because what we're going to do is we're going to pick a log to work with. Doesn't matter what log you perform. Here I might just go ahead and do the natural log because that would just be ln. It would be less writing. So the natural log of the left-hand side 2 to the power of x plus 2 is equal to the natural log of the right-hand side, which is 5 to the power of 2x minus 3. And the question is, why does that help, right? Well, what this allows us to do, if you recall back to your 5.3 notes, when we were expanding and condensing expressions involving logs, is we have this property up at the top. This is your power property. And this is actually the third bullet point of your notes today, which says that if you take a log of an exponential, you can take that exponent, you can actually write it in front of the log, okay? This is one of the things we did whenever we were expanding and condensing logarithm expressions back in lesson 5.3. And so if we go ahead and apply that here, we're going to be able to take the exponent that we have here, which is an expression, and the exponent that we have here, which is also an expression. We can go ahead and write that in front of the log. And so that gives us the ability to go ahead and rewrite the left-hand side as that expression x plus 2 times the natural log of 2. And that gives us the ability to write the right-hand side as the expression 2x minus 3 times the natural log of 5. And so what that does is it gets that variable x out of that exponent territory and more in front of the log so that we can start doing some divisions and that kind of thing to get x isolated. Now, as my helpful tip to you here, instead of having to work with the logs in the way that they're currently written, what I might recommend that you do is reach for a calculator and get some decimal expansions for the natural log of 2 and the natural log of 5. It's just going to give you the easiest time to be able to perform the rest of this calculation here, because if you're strictly working with the algebra and the logs of 2 and 5 here, the algebra is going to get really, really heavy and complicated here. So we're going to go ahead and reach for the calculator here. We're going to perform the natural log of 2 and then the natural log of 5. And keep in mind, if you had chosen to do the common log here, then in the calculator you would be doing the common log of 2 and the common log of 5. The very ending result will be the exact same no matter which log you pick. So we're just going to pick these here. And so the natural log of 2 we see is going to be 0.693, and then the natural log of 5 is going to be 1.609. So let's go ahead and get those written down here. So there we go. And then we'll just copy down the rest of the equation as it looks. So again, being able to trade out those logs for the decimal approximations for both is going to give us the easiest time to solve the rest of this, because what we're now going to do is we're going to go ahead and take those numbers and distribute into those expressions. And working with these decimals is going to give us a way to kind of work with that so that the algebra doesn't get as ugly. These decimals are not going to be the nicest in the world, but we have the calculator to keep track of those decimals for us. And so that's not going to be the worst thing in the world for us to keep track of here. So when we distribute on the left-hand side, we're going to get the 0.693x plus, and then we want to do a 2 times 0.693. So we can go to the calculator, do a 2 times 0.693, and that's going to give us 1.386. So 1.386. And then on the left-hand side, we're going to perform that distributed property there as well. So we want to do a 2 times 1.609, and then we also want to do a 3 times 1.609. And then we're going to get these numbers right here. So that's going to be a 3.218. So we'll say 3.218x minus, and then that second number, that would be a 4.827. So again, I know that these decimal numbers don't look necessarily the neatest here, but I promise you that working with the algebra with these decimal numbers is going to be a lot neater than having to work with the algebra with those natural log of 2 and natural log of 5s up there, okay? And so now what we want to do is go ahead and isolate x, and so the way we'll do that is we'll just go ahead and point out all the terms with an x next to them and get them collected on one side, and then everything else without an x next to it, we're going to collect those on the other side. And so we can go ahead and do that easily by subtracting the 0.693x from both sides. And then we'll just go ahead and knock out 2 birds with 1 stone here. We'll just go ahead and add the 4.827 to both sides. And then we'll use the calculator to keep track of what these decimal numbers actually are going to turn out to be here. So on the left-hand side, we're going to have those 2 numbers added together. So that's going to be a 1.386 plus a 4.827. And that's going to give us 6.213. And then on the right-hand side, we have those decimals dealing with x there. And so we're going to go ahead and say here that that's going to be 3.218 minus 0.693. And that's going to give us 2.525. So make sure I've got that copied down right. That's right. Okay, so 2.525x. And then, of course, to go ahead and solve through the rest of this, we're just going to simply go through and divide on both sides by that 2.525. So again, I know working with these ugly decimals is never ideal, but it beats the alternative, right? So we're just going to go ahead and do our 6.213 and divide that by our 2.525. And then we're going to end up getting this answer right here, which we'll just go ahead and round to 3 decimal places, just like we have in all of our previous answers. So that's going to be 2.461. Oops. See if we can get that back there. There we go. So 2.461 will be our final result, okay? And I just want to make an extra note about this problem that if you were to reach for the calculator and check this result using the whole store function of your TI-84, because we did this step right here of rounding the natural log of 2 and the natural log of 5 and got those decimal approximations and then use those to calculate further, what it's going to end up meaning for your checking later is that you're not going to end up with numbers that are identical, but they should be really, really close. So if you were to try to check this one in the calculator, just be on the lookout for that. So that takes care of all the examples in the notes today where I wanted to go through and solve some equations. The last example that I want to do for the video here is actually to go ahead and solve this word problem. So if you read through it, it says that they're relating a dollar amount, y, which is in billions, to a number of years, that's t, okay? And they're relating those using this equation right here, which relates y and t. So that is a log equation there. And then they go ahead and do a further little bit of explanation here, and they tell us that if you have t is equal to 0, that corresponds to the year 2000. And so in part A, they just say, what was the total U.S. currency? So in other words, if we're translating that, when they're asking what is the total U.S. currency, they're asking for the dollar amount. So they're asking you what is y in the year 2012. In 2012, since t equals 0 corresponds to 2000, then that means that t would be equal to 12 if we're in 2012. So literally all we're going to ask you to do here is take your equation, which says y is equal to negative 611 plus 507 times the natural log of t. We're just going to ask you to plug in your t value, which is 12, corresponding to 2012. And the nice thing about that is because everything on the right-hand side is something that you could plug into the calculator straight up, and it'll give you the actual answer here. So let's go ahead and do that. So negative 611 plus 507 times the natural log of 12. That's going to give you this decimal approximation right here. Keep in mind that's your dollar amount. That's y. That's in billions of dollars. So I'm just going to round this up to the nearest billion. That'll be $649 billion, which is an incredibly large amount of money, right? So $649 billion. That'll be how much money there is in 2012. Okay? So that's pretty good. So in the next question, it says, in what year? And so just kind of pausing there, if they're asking you what the year is, now they're asking you what t is equal to. Did the currency in circulation reach $7 billion? And so that's asking you what is t when y is equal to 700. So we're going to go back to that exact same equation, and instead of y, we're going to replace that with a 700. So 700 is equal to negative 611 plus 507 times the natural log of t, okay? And now your goal is to go ahead and solve this equation for t. We can go ahead and do that by doing some inverse operations and getting that logarithm completely isolated. So on the left-hand side, I've got a 700 plus 611. It's going to give you 1,311, and that's going to equal 507 times the natural log of t, okay? Continuing to get that log isolated, we can now just go through and divide both sides by 507. And I'm just going to continue over here where I got some extra room. So if you do that on the left-hand side, the 1,311 divided by the 507, that's going to give you a decimal number that's approximately equal to 2.587, blah, blah, blah. There's more numbers after the decimal point there, so we'll just go ahead and jot that down here. And that's going to equal the natural log of t completely isolated. And the reason that this helps, again, is because we've talked about in your 5.2 notes how you can change this logarithm equation and rewrite it using the language of exponentials. We know that the base of this logarithm is an e, and so we know that we can convert this language over by starting off with a base of e and then looping this around. So e to the power of this number is going to be equal to t, okay? So t is going to be equal to e to the power of that number, 2.585, blah, blah, blah. And that's something that we can get into the calculator right now, okay? So let's show you how to type that in, right? So we were taking a 1,311 and dividing that by a 507, and that's going to give us this decimal number right here. And what we're doing now is we're doing e to the power of that answer. And so keeping everything nice and fresh in the calculator, we're able to get a nice exact answer here. And so it looks like it's going to be just a little bit over 13 years that we're going to be, I'll say here 13.3 years if I round to the nearest tenth. We're going to be reaching up to a dollar amount of 700 billion, which is My goodness, such an incredibly huge amount of money. So there we go. That'll do it for this video. I just wanted to go ahead and show you a couple of different examples where we have an exponential equation. So hopefully that all makes sense. If not, feel free to always reach out. Always eager to answer whatever questions you have. But that's all I have for this one. Thank you very much for your attention, and I'll speak to you in the next one.